I'm going to start off with a very, very simple set of things that are easy to sort out, and then I'm going to do some more complicated stuff, and then I'm going to look at the really hard stuff. So the simple stuff should be relatively brief, but there's some new things that we've discovered over the year that, yeah, it's a nice, little nice tweaks that we've managed to find out. So what I want to talk about is how we're going to push the limits of terrestrial weak signal DXing. So this is specifically about digital modes going through bits of atmosphere. There's going to be, I think I did a count up, and there's about 70% questions rather than answers. So it's an open-ended discussion. So most of the answers I'm going to give you are simple. Unfortunately, the questions aren't. So here's the big question. On the display, I can see this damn signal. I cannot decode it. What the hell's going on? I can hear it. It's loud enough to hear. I've had, I think, on Zello, probably a dozen conversations with people who have been tweaking things. So this is really, first section is my experience of what was wrong and how we fixed it. So, yes, people do tend to say it's the digimode's fault. So, looking at, to start with, finger trouble. Things to do with levels. Filtering or not filtering. What to do about interference, and some new stuff about timing. First question then, nice easy one here to start everybody off. How many times has somebody said, I can't decode it? Are you sure you're on the right mode? Oh, well, I think so. Oh, I didn't click on the box that said sub-mode. No, sorry, I'm on the wrong mode. How would you know that? Well, if I'm looking at the display, I need that information. So on the marvellous WSJT documentation, it does actually have some useful information about how to identify it. But SIG ID Wiki is a thing to look at. If you have a look at SIG ID Wiki, if you're feeling really keen, please add some information to it, because they haven't got all of the recent modes. Sometimes reading the manual, really helpful. It tells you the keying rate. So if you've got something that looks like that, you can work out, oh yeah, that's probably FT8 because it's 6 and a bit per second. So if somebody's on the wrong mode, that's one way of telling. Another way is to have a look in this other very useful table on the Joe Taylor website, which tells you tone spacing. So you might have got a signal that looks like that, and I can't remember who it was, but I can't decode it, mate, can't decode it. Ah, yes, you're on the wrong sub-mode. So that's another nice, easy trick. About levels. Now, a lot of people have been told that on receive, you should set it to about 30 dB on the slider on WSJT. Well, you can do if you like, but that's probably something that works on HF. I tried to see what the efficiency of decoding was with a noisy signal. I got the slider down to 0 dB, and I thought, well, that's still working. So I went down lower. I actually went down, I think it was about minus 80-something dBm, and the noise was still, it was still decoding. So don't believe what it says on the website. For VHF, I think you can probably run it at 20 or even 10. The reason for doing that is that it increases the maximum signal we can hear. If you happen to have G8, GXP line of sight from you, when he swings the beam my way, there's a little bit of a difference. He's a little louder than some of the other stations. And trying to get that, is that me popping or is that something else?
On your leg.
In your Don't know. How's that? Is that all right? Is it me walking about doing it? I'm generating static electricity. That seems to have stopped it. That's good.
Highly charged.
Yes, absolutely. So when GXP turns his signal towards me, things tend to look a bit more like that. And it's kind of difficult to decode once it goes into the red. If you go a little bit higher than that, terrible, terrible things happen. Don't know. Somebody will have to come and interfere with me while I'm talking. There's definitely something going on. So they always say turn AGC off. Now, why do they say turn AGC off? I'll try and stand in still. I like waving my arms about. If you don't, then what will happen is that as soon as it hears one of these loud signals, it's going to make everybody else quieter. Now, that's on my system there with actually GXP. Don't tell him about the harmonics. You can see there's a little bit of suppression there, but that's pretty good for a signal that was very, very close to the top. So make sure your AGC's off. Now, what's happened is that people have said, yeah, but I can't turn my AGC off. So find ways of fiddling with the gains and any sorts of level controls that you've got to adjust the balance. It's all about balance and getting not too much RF, not too much IF, and getting the right levels of AF. So that's a nice, simple thing. That's a quick demonstration of what an FT8 signal looks like when it's been through an SSB filter. Now, you'll notice that most of the energy is in this bit here, but if you look at the FT8 spectrum, it's pretty wide. Now, does that matter? Well, not for weak signal, because you're only interested in that little tiny bit at the top. You're only going to be a few dB above the noise anyway. So make sure that if the receive side is set up properly, your problem is that the transmit side might not be. So ask the DX station, are you actually using RIT, or are you using what's it? It does it when I do that? No, well, that's what's going on. I mustn't do that. But in general, on receive side, set your receive filters as wide as you possibly can. It's not helping the receive program at all. If the DX station has got a problem and you can't decode him, have a look at the shape of what's coming through. If you can't see one of the tones, or if there's something else going on with the shape of it, make sure that he's using tones in the 1500 hertz range. Now, the way to achieve that is to use split. So you need to set it up to use fake it split with cat. Now, I'm not going to explain that because I might have to explain it again this afternoon. Yeah. So the other way is you can actually just manipulate the transmit frequency. So I'm making the assumption that you all came to the talk last year or this afternoon, and you're going to be able to do that anyway. So that's some of the nice simple stuff. Interference. I did a quick test to see what happens when you put a 100 dB signal in, and guess what? If you put a 100 dB signal in with no filtering at all, it wipes out all the signals on the band. Stick a notch in, and suddenly you can decode them again. So don't be afraid to use notch filters for strong interference tones, or GXP. Now, here's one of the things that's changed. I think probably last year I said the Windows time is pretty horrible stuff, but we've done some really careful tests, and if your time is incorrect by 1 second, it's going to push the number of stations that you can receive down, because if they're 2.5 seconds off from you, you're not going to decode them. Minus 2.4 and plus 2.5 decode perfectly. But if your time is off by a second one way, there's going to be people who are a couple of seconds off the other way. Everyone else will decode them and you won't. So make sure your time is spot on, and recommend to everyone else that their time's spot on. How are we going to do that? Press a button on it or not? Ooh, there we are. There we go. So the thing is about this that nobody realizes that their time's wrong until you tell them. So don't be afraid to say the DT setting on yours. See that DT column there? If you know your time's right and the other station's wrong, then it's always polite to tell them. Is my clicker not playing now? Honestly, technology. There we go. So last year I would have said, yeah, Meinberg is the way to do it. It's perfect. It does the job brilliantly. However, it comes with a nice GUI, pretty pictures. You can do all sorts of stuff with it. But for some reason, I must have had 6 or 7 people over the years saying, oh, I can't get it to work properly because reasons. So if you're running Windows 10 and you can't or won't run Meinberg or Dimension 4 or whatever it is, the Windows time service isn't actually dreadful anymore. Just make sure you're using sensible pools. People tend to use what comes out of the box. Make sure you set your time to be using the right pool.ntp.org, things specific to the UK. You won't go far wrong. So Windows Time Service is currently still using SNTP, but they've tweaked it, and now there's a load of registry settings. And if you look at that, I'm, 6.4 milliseconds out. That's after about 3 or 4 days. It hasn't really gone off at all. It's been nearly as good as Meinberg. So I've put on my website, I'll put all the details about this, so you don't need to make any notes. The important changes, you need to set the polling rates, so the max and min polling rates, and the slewing rate for when it finds errors. As I say, those are the sample configs, which will be up on my website shortly. So, everything's looking great. We've done all the simple stuff. We're doing brilliantly. Can't decode the damn signal, though, so there's something else going on. So, is that because actually tropo, VHF and UHF and SHF DXing is harder than EME? Yes. There's a lot more atmosphere to go through when you're trying to do extreme range terrestrial than there is when you're trying to get to the moon. Unless you're trying to do sub-horizon on 10 gig to ZL, of course. But, so, ultimately, most of the effects that are messing up the decoding of digimode signals are to do with things that are happening in the atmosphere. The usual thing people say, well, is refraction, diffraction, reflection, interference, and scattering. Well, they're all sort of related to the same thing. There's multiple paths out there. Things combine and cancel. You get phase changes, you get amplitude changes, and it messes the signal up. So things fade in and out. So really, there's almost 2 separate classes that affect it. They're a matter of scale, but you've got coherent reflections, things that you can predict for the next 100 milliseconds or 30 seconds, perhaps. And you've got non-coherent things, which are stochastic random processes. So in those, I'm putting aircraft scatter as being reasonably predictable, meteor scatter as being a bit predictable, multipath reflection and ducting and sporadic E, pretty predictable, second to second. Troposcatter, aurora, ionoscatter, and hydrometeor scatter, I think we can say pretty much stochastic processes. You can't say what the phase is going to be in a millisecond's time, never mind in a minute's time. I think, based on my experience of 2-meter FT8 users, the primary cause of all the decode problems is aircraft scatter, but they don't know. And a lot of people have never really looked into the detail of what is going on with aircraft scatter. So it's probably, the main effect is between 200 and 600 kilometers. So it's on those relatively small stations who are running 25 watts or 100 watts and to a small beam, and they're really having a struggle getting to 600 kilometers and don't know why. Aircraft reflection is really not scatter, it's really specular reflection, I think it would be fair to say. If you look at the papers on biostatic passive radar, you're probably getting all sorts of watch lists, but there's a lot of information in there. In general, aircraft scatter doesn't last very long, so we use fast modes on there, but in a slow mode, it tends to mess things up. So that's just a look at the GB3 MCB beacon from 460 kilometers away. You can probably see the tropo signal in there somewhere, but all of that I'm receiving during the day is all aircraft scatter. So there's a fair amount of Doppler on those signals and some pretty loud bits coming through there. There's a bit of amplitude and phase flutter, but it's not an entirely random process. So people say, ooh, a lot of QSB on your signal, old man. Well, actually, no, there isn't. What you're hearing is lots and lots of aircraft. So this is what we've got to try and fight against. So using the very wonderful Air Scout, you can look at the track. So this is down to the beacon. You can find out where the plane is. So there's that little bit. Oops, there, that's where the plane is. And there's all the mountains between me and MCB, which is why I don't get the direct signal. So the signal's going up from me at about 0.6 degree above the horizon and hits the plane and bounces down to, sorry, the other way around. The signal comes from them at 3.3 degrees and lands in my receiver at 0.6 degrees. So there's not, there's no problem with ground flutter. It's a lovely direct path, which is why they're so damn strong. However, because that plane's moving, this one particular plane was moving at 427 knots, and That's 220 meters a second, but it's traveling at 26 degrees to the path, so it's what, about 28 meters per second or something? That gives you a Doppler shift of 12 hertz, which is 2 complete tones at FT8. So is there any wonder that it messes things up? Unfortunately, FT8 is one of those modes where we can't fiddle with the spacing. So what does it do to other MGMs? Well, it depends on what mode you're using, because some of the modes have AFC built in. Unfortunately, for some reason, they didn't build it into FT8. Nobody's quite clear why. You can expect planes not to be traveling much more than about 500 knots or so. Occasionally, you do get a fast jet going through, and that gets quite exciting. But around about 2 hertz per second Doppler means that during the course of your transmission that you're trying to decode, the frequency's moved 25 hertz. Well, FT8's only 50 hertz wide, so that's going to cause us some interesting difficulties. JT65 actually has AFC built in, so you don't have a problem, much of a problem. So there's a contact, that's one station, apart from the smear over at the right. All of that was from one station, and none of it is the direct signal. I think it was actually GI6ATZ. So look at the amount of overlap you've got there. What hope have we got of decoding when the tones are interfering with each other? So they're at different phases, they cancel out, all sorts of things going wrong. The rates of Doppler on there, you can see the curve. It's moving probably not particularly fast. I think most of those planes were on the glide path into East Midlands Airport. I was beaming south at the time, and GI6ATZ is northwest of me. So I was getting plenty of decodes. So I looked into why this was. So quite often, for real DXing, you might find that aircraft scatter's a brilliant thing because you've got this huge signal coming through. It's moving about the place. So why can't I decode it? Well, it looks like it's Joe Taylor's fault. So I like this particular thing. With sufficient motivation, it will not be very difficult to add AFC capability to an FT8 decoder. Yeah, I think that was 3 years ago, something like that. Yeah. So can everybody just please keep asking on the WSJT Devel list, please can we have AFC for FT8? Because it would actually be useful for those of us who use VHF, UHF, SHF. Meteor scatter pings. Now, are meteor scatter pings a problem? Well, actually, no. If you've got enough meteor scatter pings to mess up your decodes, turn off your radio, turn the other radio on, and go and work some FSK, work some proper DX by a meteor scatter. So there are some hilarious things that I've seen where somebody's decoded a signal from OK or OE or somewhere like that on their little white stick aerial, and then for the next 3/4 of an hour, they're trying to reply to it. So, yeah. But the other thing that we have found is that where there's if I'm going across the North Sea in the mornings to OZ and so on, quite often I'm getting a lot of meteor scatter on that, which is backscatter effectively. So I'm actually beaming down across. If I want to work them, I have to beam at Norway. But if I'm trying to work them direct, I'm getting side scatter MS, and that is messing up my decodes. You can probably take 3 pings or so during an FT8 transmission before it stops decoding. Not really designed for this sort of thing. So what happens if there's ducting? Well, ducting gets very exciting. There's a phenomenon that affects me particularly, where if I beam to the east when I'm trying to work a station to the south, the tone goes higher and higher and higher. So I'm talking to somebody and it starts sounding like Mickey Mouse as I swing the beam round. And what that's caused by is probably a change in the refractive index of the troposphere, where the fog's lifting or the sun's risen and it's heating the layers and it's moving up very slowly like this. But it looks like it's superluminal velocity. You know, this thing's running at twice the speed of sound according to the Doppler. So the reason is that if you imagine a layer that's almost flat but not quite, and it just moves up a little bit, it doesn't need to move very far for the effect of that to have travelled 50 or 100 miles. So it's all about the geometry. So yeah, if you're starting to get ducks, just go and chase tropo DX instead. So let's have a look at the incoherent scatter. So here we've got a test signal that I put on from a local station, and these two graphs are on the same scale. That's 150 kilometers away on 3 centimeters, and that's a troposcatter signal. That's a fairly direct line of sight signal. So you can see the amount of spread on that is quite spectacular. But also look at the shape of it. So it looks almost like a bell curve, a normal distribution. Point about this is that that is just not predictable. I can predict on that there what the phase is going to be and what the amplitude is going to be in a few seconds' time. On this, I couldn't tell you it within a millisecond. So troposcatter works by, well, everybody knows how troposcatter works. 1964, Sunday did a smashing paper. If you've got a geometry like this where you've got 2 stations, a few hundred kilometers apart, there's a common volume where both of their antennas are radiating. This here is the horizon line at this end, and the horizon line at the other end. The bottom half is chopped off because obviously where you've got a VHF beam, the first lobe is not pointing horizontally, it's actually pointing slightly above the horizon. So up in this sort of zone, you're getting a beam-shaped blob from the one transmitter, and the receiver is looking, and it's got a beam-shaped blob. Those two sort of merge together to form a common scattering volume that's got different densities, it's got different path lengths. So, are you going to click on? Go on, click on, you miserable thing. Okay, so a lot of words on there, you can read that one later, but basically what's happening is that signals are reaching this common volume, and there sees tiny little changes in the density, in the pressure, in the temperature, amount of dust, amount of moisture, which cause little bits of refraction. And because of that refraction, one of the wavefronts will be going slightly off that way, and one will be going this way, and then there'll be more of these. They all compound themselves together, and eventually you get a pretty much random distribution of phase and amplitude and direction. There are some wonderful models. If you're ever feeling that you can't get to sleep one night, just have a look at those ITU papers, marvellous things. And this is called Rayleigh fading. It's a scale invariant fading, so it's happening at scales from probably milliseconds to minutes. And it follows almost a Gaussian curve. Now that's going to be quite useful if we're thinking about how we're going to decode this. So there's a nice 10 gigahertz JT4 signal from about 300 kilometers away. And you see the amount of spreading on it, about that much, whatever that is in hertz. It's not excessive, it's 30 hertz, 50 hertz, something like that. And the JT4 decoder will actually decode that. So one of the things you've got to think about with selecting the right mode is, am I at a point where this tone is going to hit that tone? And the decoder's not going to be able to know the difference. So you need to think about tone spacing. That one decoded perfectly. So I stuck out a signal on 10 gigs from a site 150 kilometers away to me. And what should happen is that I hear a nice pure 639 hertz tone. What actually happens when you look is not a nice sensible sine wave, but that. So that's the actual 639 hertz signal. A bit random. So let's have a quick listen to what that's like. Now, I want you to, those of you who are CWI operators, I want you to decode this, please. That's enough of that. Come on. Spectrum, when you analyse it, looks like that. It's a good sharp peak. So actually, although it was hard for us to hear what was going on, the DSP in the receive program can pull that out quite easily. Zooming in a little bit, that's the shape. That's that bell curve again that we've seen before. It's an entirely flat band, and the width of that would work quite well on a lot of modes. But you try an FT8 on 10 gigs on that, no chance. So I ran an autocorrelation to see if there was any structure within that tone, because I was damn sure I could hear something. And the autocorrelation just had noise. I couldn't see a thing. So then I put in a delay between the signal and the two inputs to the analyzer of about 1/638th of a hertz, so 1.57 milliseconds delay. And I got that nice little peak. So there's definitely something there, but you know, there's not really any obvious structure there, except, you know, there's some little bumpy things out here. It's about, well, maybe around less than a hertz anyway. So there's something going on. Just have another quick listen to that. Pure random noise. It's amazing what you can hear. I wish that thing would work. Come on, stop pressing around. So you'll have to, if anybody's interested later on, you can have a look at that. That's the Spectrum Lab that I used to make it work. Good piece of software. So let's have a look at that zooming out. What I did here was, it's catching up with me now. Come on. Oh, what fun this isn't. See if it will do it this way. Are you going to play? There we go. So I tried zooming in just to see what would happen at different scales. So that's looking at that signal at the amplitude of that signal at 12 seconds, and then at 1.3 seconds, and then at 0.5 seconds. It looks the same. So that's pretty certain that it's a self-similar Gaussian random stochastic process. So then I had a quick look using MATLAB. Now, everybody needs to use MATLAB. It is a fantastic tool. I'm not going to dwell on this, but it's marvelous. I imported this WAV recording into it to have a look. There's the little MATLAB program that I used. And there's what it looks like. So it looks like moderately random. But those are the hum components that I expect to see at 50 and 100 and 150 hertz. But what are these? Interesting. So there's a big component at 1.05 hertz. So other ones at 4.5 and 9 hertz. Have I discovered something? Is there something fantastic here? Except I tried to repeat the experiment, and there were no LF components at all. What the hell's going on? It's actually the wind farm turbines. When I looked at it, the wind farm turbines, yeah, they were going at full speed, which is exactly 3 seconds per rotation. Yeah, I've got a lot of wind farms. I'm just going to play with this now. Is it hell? That's what it sounds like at my house when you're trying to listen to almost any signal. You can ask John Drew3SQQ about that. So, yeah, don't even go there. So that's another interesting effect that people don't think of that might affect their digimode decodes. So, plenty of stuff on the web. Go and have a look at it. That's a marvelous document. You really enjoy that one if you can't sleep. So, it's all about picking the right mode for the conditions. If you've got more than half a tone spacing of shift or spread during a transmission period, you need a wider mode. Sometimes you see all stars of the actual dB. That's when it's getting very close to the limit. If you start seeing that, spread out, use a wider tone. If you've run out of tones, yeah, we need to talk to Joe Taylor. So, if it's chopped up because of the random processes, try one of the JT9 fast modes. Anybody use JT9 fast for anything? Not a lot of... Oh, yes. So, oh, John, right. JT9 fast modes are really good for aircraft scatter and other sorts of short-term fading. So give them a try. Also, why not try the moon bounce modes like QRA64? It just might work. Would it be nice if we didn't have to do all this choosing? Rainscatter. Quick run through of Rainscatter. It's just like the other scatter modes, except because of the way Rainscatter relates to rain, it's patchy. So you get peculiar shapes. Instead of a nice rounded Rayleigh curve, you get all sorts of weird and wonderful stuff. I had a quick play on 13 sems to see what was going on. I heard a bit of Rainscatter, thought, oh, I'll try 3 sems. Trying to get through to, because normally when I'm playing on 3 sems, I just send my call sign as tones, you know, like you do, graffiti. But I had a go, I saw this nice reflection coming through on 3 sems from Mo Cop. Nobody else was around. So I looped it back, put it into another instance of WSJT, and I switched to FM mode. So I was running FT8 over narrowband FM over 10 gigahertz Rainscatter. Absolutely brilliant. Just give it a try. If you can find a QSO partner, if people say FT8 does not work on 10 gigs, go for it. We ought to have a DX table for that. So if you look at Rainscatter, it's doing all that sort of stuff. That's about, about 40 minutes of transmission. It's almost like a 3-dimensional sort of thing that you're seeing as the rainstorms come through. So imagine trying to tell your digimode program how to decode that. Anyway, the practical effect is that pretty much the other modes like ionoscatter and aurora, they do the same sorts of things, but the shape of the curve's different, the characteristics are different. I think we might have an auroral. Yeah, so aurora tends to sound a bit buzzy, it's because the shape of the reflection is slightly curved, so you need a different way of decoding that. Anyway, so this is all you've got to do now. Humans, we need to get a DX station to send us a long carrier. We need to analyze it in Spectrum Lab. We look at the shape of the Rayleigh fading. We look for the characteristic details of it, any weird things. We do some MATLAB analysis. We get the DX station to send chirps. We do more MATLAB analysis. And then, right, OK, we've got it. We'll pick a mode. Brilliant. Oh, dear. We weren't fast enough. So what can we do about this? Help may be at hand in the future. Yeah, OK, people will say, yes, but people can work 4,996 kilometers on 2 meters without too much trouble at all. Well, yeah, because they're using a mode that's not got all that randomness in it. They're using a bit of tropo at one end, pure ducting, and was it sporadic at the other end? So, you know, absolutely the sexiest thing around is linked modes, but it's actually not that hard at extreme range. It's the medium ranges that get tough. So, here's the hard bit then. We've fixed all the simple things. We know a little bit more about the challenges of why these things are not altogether easy to decode, and we know how to pick one of these submodes to match the path characteristics. Humans cannot do it fast enough. So, wouldn't it be nice if there was a way of doing that? If only there was a technological solution. Aha. So, EME ops have used single tone for years on end. It's great, except your payload consists of 1 symbol per period. You know, you could say my call sign will be on 1,274 hertz, and if you hear a signal on 1,282 hertz, that means I'm sending you a report of, yeah, it just seems like cheating to me somehow. We could use QRSSCW, and I don't know if, has anybody used QRSSCW? Yeah, so that actually, on most of the microwave bands, that actually works quite well if you leave the thing to decode for long enough. However, we're not talking high speeds here. This is Spectrum Lab, and you'll notice you can go to 120 seconds a dot. You can do 600 seconds a step, but you're going to be there all night. So although it will work, it might not be the most optimal way of doing it. Can we use slow JT9? Well, short answer to that is no. And the reason for that is that I think in the documentation, it says important things like it can tolerate a drift of up to 0.2 hertz per minute. or 0.05 hertz per minute for JT910. If you ever play on VLF, have a go with this because it is fascinating stuff. A QSO, one side of a QSO takes, I think, anything up to about 16 hours. Is that right? Something like that anyway for some of the longer convolutions. And I like this thing. Ionospheric instabilities can thwart successful decoding. I think I ought to have that on a T-shirt. So that's not going to sort us out. It's JT9's a bit of a kludge. They took the existing JT9 and just slowed it down, so it needs a full recode, really. Yeah, I mean, it's superb. Yeah. I tend to use things that are designed for things that they're not supposed to be used for. So how are we going to deal with this? Well, can we somehow use, like we do at the moment with Zello or 2-meter talkback, and say to the other station, can you just tweak it a little bit this way, that way? Can you just try elevating the dish a little bit? Can you use a wider mode? Can you do whatever? Change frequency. We use it for tweaking things, looking for scatter points and so on. Wouldn't it be nice if there was a way of slightly automating that? Now, imagine that we could find some software that doesn't exist yet, but automated that path sounding analysis process and maybe looked at frequency and spatial diversity as well. It could look at all of those spreading, fade rates, interference, Doppler. It could look for co-channel traffic, all sorts of things that you could actually dig out from it. Could even work out if you've got troposcatter, quite often they use angular diversity. So you could, for instance, have electronic steering of your transmit beam if you're using, certainly on the higher frequencies. So rather than actually moving your antenna, why not have a phased array and use that to steer the beam around? You could tell the far end to try making variations. You could have a whole array of separate receive antennas to give you spatial diversity. You could have an awful lot of those, actually, like some of the radio astronomy people do. There's loads of academic papers about this, a link adaptation for microwave link. A lot of students, so you've got to avoid the students. But the people who've got an academic background, fascinating to see what they're up to. However, it's all about 5G or the backhauls for 5G. So you've got to take it with a bit of a pinch of salt. They're talking about something at an entirely different scale, hundreds of megasymbols per second. They haven't got any infrastructure for out-of-band adaptive feedback. I'd be happy with 100 millisymbols per second. You know, so it's an entirely different order of magnitude. Well, 8 orders of magnitude different. Can we adapt any existing amateur radio digimode software? Well, there's a bit of a problem there. The people who write the software tend to be software writers and people who've got an academic approach. They're not necessarily aiming at anybody other than HFers and EMEers, because that's where the main market is. And until recently, they haven't got that much interest in the SHF end of things, and certainly only a little in VHF. So we've got a bit of a barrier. So if we want to push the limits, we're going to have to try new ways of doing this. And it's not going to be easy. I said this was the hard section. So when I discussed this with people, I got these sorts of responses. Oh, we've already tried that and it didn't work. Ofcom have said to us, you've got this new bandwidth. We don't want to do more of the same. So people then say, yeah, but it'd be ever so complicated. You'd need loads of receivers and antennas. Well, what's the problem with that, you know? You'd need massive bandwidth to get this feedback. Well, are we going to carry on as we are at the moment, or are we going to try and push the limits? So I'm voting for pushing. So why not have a whole set of SDR channels? Let's not stop at 16. Let's see if we can do more. Why not allow the receive end to tell the transmitter over a back channel like talkback, but done through the computers? And why not have electronically steered beams? I told you there were a lot of questions. You know, people do this, and it does work. What was that about? An orange over the North Sea, and you could tell the distance and velocity? Yes. So why don't we use 146 or 71 megs using new packet radio, nobody spit? or another high bandwidth transport for this out-of-band adaptive feedback. Why not, if we can't be bothered to do that? Oh, there's new packet radio. There's a link to that at the end. 500 kilohertz, designed really for use on 77s, but it works pretty well on...
It's been run on 146, it works.
There we are, you see, I'm out of date already. We could use the internet. Why are we using software which still processes baseband, effectively coming out, even when we're using an SDR? You know, we're turning this down into baseband and then messing about and decoding it with a sample rate of 12,000 bits per second. Why don't we do it further up the chain, in the SDR code or in the firmware? You know, why aren't we using FPGAs to do this? There's a lot of interesting new ways of doing stuff, but certain people who generate this software are using janky old bits of Fortran. Yeah. I left that behind a long time ago. So, you know, why not learn Verilog? Verilog is very cool. But all the VHDLers, I'm sorry, but Verilog is cool. How are we going to get some of this enthusiasm for complex tech in the makers, the hackers, the robotics people, the drone flyers, the high-altitude ballooners, the mesh radio people, and people who are doing LoRaWAN DXing? Why don't we find ways of getting them involved in radio? Because at the moment, when I talk to them, they say, well, that sounds horrible. I've got to go and talk to my local club, and they all smell a bit. And yeah, so see gatekeeping, yes. So, whoops. Sorry. So get the basics right. Get your station so it's absolutely tuned up. Every last 0.1 of a dB is going to help. Don't tell me off about new packet radio. I was a sysop of a DX packet cluster for far too long in the 1990s. I've still got the twitches. Have a look at MATLAB, and particularly the free version Octave. 4 lines of code, you can do a fast Fourier transform on a WAV file. You know, what's wrong with that? Brilliant idea. Don't believe things that wise old people, particularly like me, say things don't work. Because when wise old people say things don't work, they probably will do eventually. So just remember as well that whatever you do, you're going to be enjoying messing about. You're going to be learning stuff. So don't reinvent the wheel. Let's try some new stuff. But more importantly, go and make some noises. I hope everybody's identifying all those. MSK 144. Thank you very much indeed.
Thank you, Neil. We're a little bit pushed for time, but can I take one question, please? Am I bid for one question for Neil? Right, here we go.
Mike G for CDF. I'm fairly new to digital modes, and I've worked FSK 441 and FT8 and JT65C. But the problem is there are frequencies that seem to be allocated to these specific modes. If you've got a local station that's filling that frequency, you really want to go to a different frequency. Anybody thought about having multiple frequencies for different modes so you know what to go to and what not to go to?
That's my answer as the VHF manager. You can always transmit MGM over a whole space over the bands. There is nothing, even in the band plans, that says you must use this frequency. Some of the frequencies given in the guidance are wrong, actually, for the things. If you use a meteor scatter mode, it's easy to work split. You just put in your CQ 377, your call sign. Likewise, if it's by arrangement, or even on FT8, you can go CQ, different frequency, move there, nice quiet place. Split operation works on all digital modes.
Yeah, no, I think also if you happen to be writing the software and you accidentally put in a frequency which happens to be in use for, let's say, VHF talkback for microwaves, then everybody will suddenly move there. So, you know, the Americans put in the code 144174. That really messed up 144175. So we had to move.
It's been a long and very sore debate over the last 7 years, and Joe Taylor stopped speaking to me about 50 megs many times ago. So, thank you very much, Neil, for giving a really enlightened talk. He's on again after lunch, but this is a slightly different FT8 and getting used to it presentation. So, thank you very much again, Neil. Let's say thanks in the usual way.